Good morning. My name is Captain P.S.V. SAGAR. I am Associate Professor here, handling the topic of bridge equipment and bridge resource management 3 for second year students, even semester. Presently, 4th semester. The first topic I will be discussing is ECHOSOUNDER. In this device, which is an electronic device placed on the navigating bridge of the ship, we use this equipment to find out the depth of the seabed from the bottom of the keel of the ship. Why is this needed? In order to know what is the depth of water under the keel of the ship, so that no damages occur and vessel is saved of any problematic situations like grounding, coming to shallow depths, etc. Starting off on this topic, we have a ship this being the keel and this being the seabed. So this is the unit which transmits the signal to the seabed and the waves are reflected, and as the ship moves, the waves are re-picked up by the vessel. This signal progressively comes up. So now, what is our intention to get the depth? And this is solved by using acoustic signals or sound signals in water, which travel at the rate of 1500 meters per second. Velocity in sea water. This being the case, our most significant issue is finding out the time it transmits, that is the signal, and the time it is received back on the vessel. This difference of time is utilized. Suppose the time of transmission is T and time of reception is T1. So T minus T1 will be equal to the duration of acoustic signal. So velocity of sound waves in water equals to depth divided by time. So this implies depth is equal to velocity into time. Considering this, the velocity being, as already mentioned, 1500 meters per second, we are calculating T minus T1. Depth into T minus T1 is equal to velocity into T minus T1 is equal to the depth. This will help us finding out the depth at that particular moment. As the ship progresses in its pathway in a seaway, it progressively keeps picking up depths on a continuous basis, and as the seabed is never the same everywhere but keeps changing, we get the availability of signals on a continuous basis into the receiver, which is then used to calculate the depth at that point. Now, what is the instrument that is used for this calculation? The instrument that is used for this calculation is called a transducer. Is a transducer. A transducer in literal terms is an instrument which is used to convert one form of energy in another form. So we are transducing one form of energy to other form. In this instance or this capacity, we use a transducer which, as I showed you, was located at the bottom of the ship on the keel plate. This is the transducer, and we use it for getting our vessel's position, rather not position, depth of water under the keel. So the kind of energy which a transducer converts is electrical to acoustic or sound in water. As we deal with acoustic waves in the water, we find that the sound signal is picked up on the return and bounces off. Now, going by the time difference, we had said t minus t1, but it could very well be construed as the total time taken divided by 2. So, we could very well say that this was velocity is equal to depth divided by time by 2. So, this is V into T by 2 is equal to depth. Why divided by 2? Because time of transmission and receiving back on the ship. That is twice the depth, twice the time. So, we calculate the time divided by 2. Okay. Now, the fact that sound waves have a particular frequency and wavelength has to be considered, and in this respect, if the frequency of the transmission is high, it leads to high attenuation. Attenuation being loss of signal strength due to the high frequency in seawater. Higher the frequency, smaller the wavelength, which we all know. So, we have to keep that in mind. Now, let us consider the different types of transducers. there are two types of transducers. They be electrostatic and the other being magnetostrict. Now, what is an electrostatic type of transducer? It is an instrument which calculates the depth by sending a sound signal from the bottom plate of the transducer to the seabed and receives it back again. What is the principle it works on? It works on, we are discussing, as I just now said, the electrostatic type of transducer. The principle that it works on is the electrostatic, or which also means Piezoelectric effect. Also known as piezoelectric effect. Considering this, what happens is we have a crystal being a plate of a particular material, for example quartz. Quartz is used in such a manner, as we all know, in piezoelectric effect, when a crystal is compressed on both its faces, it generates a current. And the opposite also is true. When a current is supplied to the edge of the crystal, it generates pressure of increasing and decreasing intensity on its faces, especially if an alternating current is fed to it. So what we have here is, if we have a crystal of quartz and we are able to feed a current to it of alternating current nature, it will vibrate. It will vibrate. This thing being considered, we all know we can take advantage of this. So the other situation is, if the quartz plate is placed between two steel plates, and a pressure is applied, a current will be generated. Knowing this, let us consider how this has been taken advantage of in the electrostatic transducer method of transmission of sound signal from the keel of the vessel to the seabed. Right. So now we have an electrostatic transducer where a steel plate, one placed above and one placed below, with a crystal in the middle, is used to being placed and a current is fed to it. A current is fed to it. By which I mean an alternating current. And so the plate starts vibrating. By which I mean because the quartz crystal is being fed an alternating current, the plates start vibrating. Now consider if the crystal is fed an alternating current which makes it vibrate at its resonant frequency, which we all know is the principle of resonance in physics, we get a situation where the plates pick up the vibration, and this method of resonant frequency will create maximum vibration on the plates, and that signal can be used to transmit a sound wave of the relevant frequency into the seawater. Having done that, the acoustic wave goes to the seabed, from where it gets reflected and comes back to the receiver, receiving transducer of the electrostatic type, and from there we can pick up the returning signal. We have found the time out of transmission to reception, that time divided by 2 into velocity. One correction here I would like to tell you: the velocity of acoustic waves in fresh water is considered to be 1500 meters per second, while in velocity in salt water is equal to 1525 meters per second. This being the case, we are able to get a situation where we have found the depth. Now, what do we do with this depth? We have found the depth in the from below the transducer, which, considering modern electronics, can be made to be highly accurate. And what do we do with this depth? Let's go to the block diagram of a transducer, and then we'll go to the magnetostrict type of transducer. This is the recorder on the bridge. This being the oscillator. Transmitting, receiving, transducer, and further on to the amplifier. So this is the block diagram of a echo sounder we have the oscillator which generates a signal at a particular frequency sent to the receiving transmitting transducer. We have discussed only the electrostatic type till now, which is then forwarded to the amplifier, where the signal once received has got to be amplified thousands of times, considering the nature of the signal coming back to the vessel, and that goes to the recorder, where the depth is recorded either in a so-called echograph or in a digital display called an echogram. Now, once we have this in place, we are in a situation where we have been able to get the depth of the seabed under the keel, which will help us in navigating the ship in safe conditions while arriving in the port, in coastal waters, while navigating in restricted waters, and other situations which require our careful handling. Now, we come to magnetostrictive type of transducers. The second type I have mentioned, the magnetostrictive type of transducer, is based on the principle of magnetostriction, as is very clear by the name itself. We have a situation where if specific metals, let us consider a nickel bar, we are discussing the principle of magnetostriction here. Let us consider a nickel bar with a coil around it. Being supplied with a AC power supply. When the power is supplied to a nickel bar, we observe that the length of the nickel bar will expand at both the requirements, that is, at the point of maximum amplitude of the wave in both upper phase and lower phase. At these points, the signal is 0, while at these points is the maximum amplitude. At both the upper and lower phase, we have the nickel bar expanding, and during the middle points in an alternating current wave, the nickel bar comes back to its original size. How is this taken advantage of in a magnetostrictive condition is our next issue. In this kind of transducer, we have a series of laminae, laminae being laminas of nickel, laminas of nickel being fine plates of nickel which are surrounded by coils and when the coils generate signals of alternating current, the nickel laminae start vibrating, and again, considering the principle of resonance, we try to take advantage of the resonant facility, and it creates maximum amplitude of sound waves towards the keel plate, by which we considering that there is a reflector plate inside the magnetostrictive considering the reflector plate, and the signals are transmitted in a wide variety of angles from the transducer element, which gets reflected towards the seabed, all heading by the reflector towards the seabed. In this way, we are able to get maximum signals heading off towards the seabed, and with the resonance affecting, we get maximum signals entering the keel plate and going through into the water and going to the seabed. There's one or two points which we have considered in these issues of electrostrictive and magnetostrictive transducers. In a electrostrictive transducer, it is called a pierced hull transducer, by which we can consider Thank you.